All right, so yet again, today is day 6, and we're going to be continuing working through our derivatives unit of BC Calculus, which is Unit 3 in the textbook. You guys ready?
Yes, sir.
Cool. So as always, we start with our topics of discussion. Yet again, I don't expect you to know what these topics are yet, but that's because we're going to be covering them today. But I hope you will know them by the end of the day. We're going to be covering some derivative rules, which is the main topic of today. In general, we're just going to be talking about derivative rules, so we can calculate the derivatives of more complex functions. And afterwards, I'll either assign some practice problems, or we can stay a little bit after and do some practice problems. But today is really just going to be about learning rules for calculating derivatives of different functions. Because you'll notice that the only function we've calculated the derivative of so far is x squared. And there's a lot more functions than x squared. So today is going to be all about calculating the derivatives of different functions and the rules that go along with that. We're going to do some terminology and more stuff on velocity as rate of change, is the topic we talked about on Friday and Thursday, I believe. But we're going to solidify that topic today. We're going to talk about the idea of sensitivity to change. We're going to derive and understand the derivatives of trigonometric functions. We're going to talk about Leibniz notation, which is actually something that we've kind of already skimmed at already. I just didn't mention it as Leibniz notation when we did it. And we're going to talk about derivatives as peeling an onion. I once heard someone say that taking the derivative of a complex function is like peeling many layers to an onion. And once we have all our derivative rules, I'm going to show you what that means and how, with our rules, we can calculate the derivative of any function we want, no matter how complex, by peeling back its layers one by one using the rules, if that kind of makes sense. All right, so the first order of business, this is probably going to be the longest part of the lecture. We have to derive some of the derivative rules. All right. So what I was thinking we would do is we would do a dynamic lecture on Jamboard where I would derive where the rules come from. I would kind of make it dynamic where I would ask you questions along the way to kind of probe the answers out. For example, I hope you guys remember from last week when we were deriving something, I would ask you guys questions like, what do you notice about this, to try and poke at the answer and have the answer come out. I'll do the same thing when we're deriving these rules. What I'll do is I'll derive them, but I'll also ask you questions to see if you guys can get the answer out on your own without me telling you it. So hopefully that is informative and also useful for you guys.
Sounds perfect.
Cool. All right. So rule number 1. Out of, I don't know how many, but it's a decent amount. All right. So rule number 1. And I got to make sure that my tablet responds. My drawing pad never responds immediately for some reason when I start the day. All right, there we go. All right, so rule number 1 for derivatives is called the I think I called it the constant. Yeah, the constant rule. All right, and the rule is really simple. All it says is that if we take the derivative of a constant, and a constant means just some number, then that is going to be equal to 0. So if we take the derivative of a constant function or a function that is just a number, it's going to be 0. And the reason that's true is because you'll notice if I graph the graph of a function that is just a number, like y equals 4, y equals 5, y equals 6, y equals any constant or any number, you'll notice it will always produce a flat line. So if I take the derivative of this function at any point, it's going to be 0. So that's why the rule works. Does that make sense?
Yeah.
Cool. So if I ask you to find the derivative of 4, that's asking you to find the derivative of f of x equals 4, you'd say it's 0. It's always 0 because it's a flat line. Does that sound good?
Yeah.
Cool. All right. The next one is called the constant multiple rule. And I'll explain it using some of the limit properties we previewed last week. All right. And that's saying that if you take a function, all right, and you multiply it by some number, let's say 16, all right, and I ask you to find the derivative of this new function, which is 16 times this function, all right, what this is equal to is equal to 16 times the derivative of the function. So if, for example, if I took the derivative of 16x squared, all right, this rule would tell us that it's 16 times the derivative of x squared. And we know the derivative of x squared is 2x, so the derivative of 16x squared would be 32x. That's what this rule is telling us. So we're going to derive it in just a second, but does the idea of what the rule is saying make sense at least?
Yeah.
Cool. All right. And it's actually very simple if we return back to our limit definition of a derivative. All right. So remember we said that the derivative of a function, f prime of x, is just whatever the limit is going to be, whatever this limit is going to be. Does that sound good?
Yeah.
Cool. So if the derivative of a function is just whatever this limit is going to be, because this limit tells us the slope and the derivative also tells us the slope, then if we ask to find the derivative of, like, let's say 16 times f of x, our limit would look like this. We'd have the limit as h approaches 0 of 16 f of x plus h minus 16 f of x. Do you agree with that?
Yeah, that makes sense.
Cool. All right, and we divide it by h. All right, and you'll notice that there's a 16 in the numerator and a 16 here, so we can factor it out, and we'll end up getting that this is the same thing as the limit as h approaches 0 of 16 times f of x plus h minus f of x over h. Right? Does that make sense how I factored out the 16?
Yep.
Cool. All right, so remember our limit rule tells us that of the limit, so what we have here is we have 16 times this fraction, right? Would you agree? Because if we put 16 on its own and we multiply it by this fraction, it's going to go into the numerator, which is exactly what we have up here. So we could say that this is equal to 16 times this fraction.
Yeah, that makes sense.
Cool. And remember what we said about limit properties. What is the limit of the product of two things? Do you guys remember?
Wait, say that. Just ask the question again.
Yeah. What is the limit of the product of two things? If we have the limit of 16 times this, how can we rewrite that using our limit rules?
I don't remember. Ryan, do you know? Let me see.
Yeah, I'm just going to erase the top part while you think about it. So here, I'll outline the general limit rule very quickly. All right. If we have,
it would be just 16 times the limit of our. It would just be 16 times the limit of
exactly.
our.
So Henry, you might have this in your notes. I don't know if I covered it. I know I did. I think I did cover it, but I don't know if you wrote it down or not. Remember when we said that the limit as x approaches some number, or as something approaches something, of a constant times a function, all right? This is equal to the constant times the limit as x goes to a of f of x.
Okay, yeah, I do remember writing that down.
Okay, so this is one of our limit rules. So we could rewrite this limit using this rule by saying, well, then this limit is 16 times the limit as h approaches 0 of f of x plus h minus f of x over h. Do you agree with that from the limit rules?
Yep.
Cool. Is anything not making sense? Anything I need to reiterate? Do you want me to review the limit rules? Anything at all?
I'm all set.
Cool.
Ryan, you good?
Ryan, you all set?
Yeah.
Cool. So we have 16 times this. All right. And what is this, by the way? Can anyone tell me what this is? What this limit is equal to? As in not the number is equal to, but what it represents.
The derivative.
Exactly. So we could rewrite this as 16 times the derivative of our function. So 16 times f prime of x. All right. Because this limit is equal to the derivative of f of x. So we just showed that if we took the derivative of a number times a function, it is equal to that number times the derivative of the function. All right, so you can pull the constant or the number out of the derivative and multiply it by the derivative of the function. And we just outlined the proof for that. Does that sound cool?
Yep.
Cool. All right, the next one is the power rule, which takes a little bit of time, but we're gonna make it work. All right, so the power rule, I'll outline what it is, and then I'll do a proof of it. All right, it tells us that if we have a function x to the n, x to some number, then the derivative of that function is going to be n times x to the n minus 1. We saw this with x squared, right? The power rule tells us that the derivative of x squared should be 2, because our n is 2, x, and because n is 2, n minus 1 is 1, so our derivative should be 2x to the 1, which is 2x. So the power rule accurately tells us what the derivative of x squared is. So this is what the power rule is saying. This is how it matches our derivative of x squared, and we're going to derive it in just a second. So I just need you comfortable with what it's saying. It's saying you take the exponent, you bring it down to the bottom, and you're left with in the exponent 1 less than what you had.
That sort of makes sense.
Cool. I'll do some more examples. So the power rule would tell us that the derivative of x cubed is 3x squared, right? X to the n. If n is 3, then we get 3 times x to the n minus 1, which is 2, 3x squared.
Okay, yeah.
That's what the power rule is saying. And we're going to derive it in just a second. All right. All right, bear with me here. All right, so our limit definition of a derivative tells us that if our function f of x is x to the n, then our derivative is the following limit. Would you agree? Because if the function is x to the n, then we take our input and raise it to the n. So instead of writing f of x plus h, if we know that f of x is x to the n, we can replace f of x plus h with just x plus h to the n, because that's the function. And similarly, instead of writing f of x, we can write x to the n, because that's the function. F of x is x to the n. Does that make sense?
Yeah, that makes sense.
Cool. So you'd agree with that the derivative of x to the n will be whatever this limit is.
Yeah.
Cool. So here's a problem, all right? We have x plus h to the n, right? We know how to expand stuff like x plus h squared, but how would we expand it if we don't know what the exponent is? We don't really know how to do that. So the best thing I can do is try and elucidate and establish a pattern, all right? And here's what I'll do. So if we have x plus h squared, all right, we know that from our binomial expansion rule, that's x squared plus 2xh plus h squared, right? A plus b squared is a squared plus b squared plus 2ab. That's all this rule is saying. Would you agree with this expansion?
Yeah.
Cool. All right. So now if we take x plus h cubed, wouldn't you agree that that's just taking this and multiplying it by x plus h again?
Yep.
Cool. So when we do that, we get this expansion. We have to do the FOIL method. So we'll get x cubed plus 2x squared h, all right, plus h squared x, all right, and then we go to the h's, plus x squared h, all right, plus 2xh times h, which is 2xh squared, plus h squared times h plus h cubed, all right? Do you agree with that expansion?
Yeah.
Cool. So then this is the formula for x plus h cubed, right?
Yeah.
All right. I'll rewrite that on another slide. It's x cubed plus 2x squared h plus h squared x plus x squared h plus 2x h squared plus h to the third. All right. All right. So next, if we took x plus h cubed, which is this, and we multiplied it by x plus h again, what would we get? We get x plus h to the fourth, right?
Yeah.
So then x plus h to the fourth, and you'll see why I'm doing this in a second, is just this times this. So we multiply the x by this, we get x to the fourth, and we take the x by this, plus 2x cubed h. The x times this is plus h squared x squared. And then we get the x. You see what I'm doing? I'm just taking the x and multiplying it by each term.
Yeah.
Then I get x cubed h plus 2x squared h squared plus x h cubed. And then we do the h's. So then we get x plus x cubed h plus 2x squared h squared plus h cubed x plus x squared h squared plus 2x h cubed. And this is really complicated, but it doesn't matter. Plus h to the fourth. So do you see how this expansion is true?
Yeah.
All right. So let's... All right. So you'll notice that there's some terms we can add together here. All right. So you'll notice we have an x cubed h here and an x cubed h here. So if we have two x cubed h's here and one x cubed h's here, then we could combine them to make 3x cubed h, right?
Yeah.
Awesome. And similarly, we have another x cubed h here, so that would actually be 4x cubed h, right?
Yeah.
So the bottom line is we could combine like terms in the expression to get x to the fourth plus 4x cubed h. We got x to the fourth. We got 2x cubed h's here, 1x cubed h here, and 1x cubed h here. That's 4. And then we have and then let's look at the x squared h squared terms. We have 2x squared h squareds here, 1x squared h squared, and 2 more x squared h squared terms, and another one. So plus 6x cubed or x squared h squared. All right, you see what I did there?
Yep.
And I get rid of all of them to let it know I've already accounted for it. And then let's look at our x h cubed terms, 2 here, 1 here, and 1 here. Let's cross them out so we know we've accounted for them. Plus plus 4x h cubed, and then plus 1 h to the fourth term, which is down here. All right. Does that sound good?
Yeah.
Cool. Let me erase. Apologize. I don't want to get rid of the bottom one, so we all good with that up to there so far.
Yeah.
All we're doing, and you'll see why I'm doing this in just a second, I'm not just doing this for the sake of annoying you guys. We're doing this to find a pattern, all right? Because if we can't find what x plus h to the n is with any formula, we can at least find the patterns between if you raise our n value up by 1 each time. So if we go from x plus h squared to x plus h, x plus h cubed plus x plus h to the fourth, stuff like that. If we can see the pattern, then we can kind of figure out what x plus h to the n is going to be. All right. So here's what x plus h to the fourth is. All right. And we showed that x plus h, I don't know why I put a 3 there. Well, I do know why I put a 3 there because there's a cube. I'm supposed to write cubed. And we also saw on the previous slide that x plus h cubed is equal to this. And if we combine like terms, we'll notice, well, there's a 2x squared h here and an x squared h here. So there's 3 x squared h's. Additionally, there's 3 x h squareds and only 1 h cubed and 1 x cubed. So we can combine like terms to write that it's equal to x squared or x cubed plus 3x squared h plus 3x h squared plus h cubed, right?
Yeah.
And additionally, we know that x plus 2 squared, all right, is just the term we had at the beginning, right? Remember, we know the formula for x plus h. I don't know why I wrote x plus 2. My bad. x plus h squared. We know the formula for x plus h squared from our binomial, for squaring binomials. We know that x plus h squared is just x squared plus h squared plus 2xh, right?
Yep.
Cool. What am I doing? All right. I'm going to rewrite it just with the 2xh term in front. All right. So, and also it's pretty easy to say that x plus h to the 1 is just x plus h. All right. So we have these three expansions here. We have x plus h to the 1, x plus h squared, x plus h cubed, x plus h to the 4th, all right? And our what we're trying to do here is we're trying to find patterns between all of these, all right? And I'll ask you the following question to see if we can kind of elucidate or figure out some patterns, all right? The first term of x plus h to the 1 is x. The first term of x plus h squared is x squared. The first term of x plus h cubed is x cubed, and the first term of x plus h to the 4th is x to the 4th. So what kind of pattern are we noticing with those first terms?
It always starts with like the x to the power of whatever's in the parentheses.
Exactly. So if I wrote x plus h to the n, if we're expanding x plus h to some exponent, we would expect the first term to be x to the n, right?
Yeah.
Cool. From this pattern. All right. Next thing, let's look at these terms, the terms with just one h in it, all right? We'll know that x plus h to the 1 has just an h here. Actually, no, we'll go back and we'll find an easier pattern, all right? I apologize for that backtrack. All right. So we found that the first term is going to be of x plus h raised to some number is going to be x to that number. All right. And that's from the pattern that we found in these expansions. I also want you to look at the last term, the h term. All right. In x plus h to the 1, it's h. X plus h to the squared, it's h squared. In x plus h cubed, it's h cubed. In x plus h to the 4th, it's h to the 4th. So what's the pattern of the last term?
It's h to the n.
Exactly. So if we expand x plus h to the n to some number, we're going to have x to the n and some terms in the middle, but the last term is always going to be h to the n, right?
Yeah.
Cool. And additionally, I want to look, the only term that concerns us, and I'll explain in just a second, is the term that has an x and only one h in it. So an x to some power and just one h in it. And I'll explain why that's important in just a second. All right. So let's try and find the pattern of these terms. All right. So in x plus h to the 1, it doesn't have it, so we're going to ignore it. In x plus h squared, we get 2xh, right? In x plus h cubed, we get 3x squared h. In x plus h to the 4th, we get 4x cubed h. So I hope you can see the pattern that as we increase our exponent by 1, the second term, the coefficient in front of it goes up by 1 each time, right? And the coefficient in front of the second term is just whatever the exponent is. Here we have a squared, so the coefficient is 2. Here we have a cubed, and the coefficient is 3. Here we have a 4th, and the coefficient is 4. You see that pattern?
Yep.
Additionally, you'll notice that the exponent on the x term for all of these is just 1 less than the exponent. The exponent on the x here is 1, which is 1 less than 2. The exponent here is 2, which is 1 less than 3. Here it's 3, which is 1 less than 4. You see that pattern?
Yep.
So that's a really important pattern. All right. And you'll also notice that the first term has no h's. The second term has 1h. The third term has h squareds. And the last term has h cubes in it, right?
Yeah.
And this is a pattern that works for all exponents. Your first term will have h to the 0, or just no h's. Your second term will have h to the 1. Your third term will have h squared, etc., 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 until we get to our last term, h to the n. Do you see that pattern?
Yeah.
Cool. And that's going to be important, and I'll explain why in just a second. All right. So if we want to find the derivative of x to the n, all right, we're taking the following limit. All right. And what we can do is, well, we know how to at least partially expand x plus h to the n with our patterns, right? We know at least some of the patterns. We know that the first term, so we can expand this, is always going to be x to the n, right?
Yeah.
And we also said that the second term, the one with only one h in it, has a coefficient of whatever the exponent is, right? So here it's 3, the exponent is 3. Here it's 2, the exponent is 2, etc. So the next term is going to have a coefficient of n, whatever the exponent is, right?
Yep.
And it's going to have an x to the n minus 1 as its x term. Because here our x is x squared and the exponent is 3, so it's x to the 3 minus 1, which is 2. Here it's x to the 1, which is 2 minus 1. Here it's x cubed, which is 4 minus 1. Do you see the pattern?
Yeah, I do.
So the second term is going to have this times h, right? You hear that? But then remember how our pattern was that the first term is h to the 0, the second term is h to the first, and then all the other terms are going to have something multiplied by h to a power greater than 2, which I'll write greater than or equal to 2. All the other terms are going to have h's in it that have a power that is either 2 or greater than 2 because of our pattern, right?
Mm-hmm.
So I'll explain why we can ignore that in just a second. All right, and then once we expand our entire binomial, we have to subtract x to the n, right?
Yeah.
Cool. So what can we say about the first x to the n and the last x to the n? Can we ignore them?
Yeah, they cancel out.
Exactly. All right. So we'll end up having this divided by h, right?
Yeah.
So you'll notice that there's an h in every single term in the numerator. This one has an h to the 1. The next one will have an h squared. The one after will have an h cubed, etc., right?
Yeah.
So we can divide each term by h, and we'll end up just getting rid of one of the h's, right? So here we get rid of the h. In the next term, we go from h squared to h because we're dividing by h. In the next term, we go from h cubed to h squared because we're dividing by h. You just kind of see why that happens, the pattern here?
Yeah.
Cool. All right, so in the end, we'll end up getting n, x to the n minus 1, plus something times h, plus something times h cubed, etc., right? Or x squared, or h squared, sorry. Because we know that as we go on each term, our h, the exponent in our h goes up by 1, right?
Yeah.
You see this pattern? So if I asked you to find the limit as h goes to 0 of this, all right, which we know this is the exact same thing as this because we just did some algebra to simplify it, all right? We would have x to the n, n times x to the n minus 1 plus something times h plus something times h squared, blah, 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 blah. So what happens to this whole thing as h goes to 0? What can we say about the terms after here? Can we ignore them?
Yeah, because they're just multiplied by 0.
Exactly. So this tells us that our answer is n times x to the n minus 1. So we answer our limit, and this tells us that the derivative of x to the n is equal to n x to the n minus 1. Isn't that cool? I think it's cool.
I think that's very cool.
Awesome. So does that make sense?
Yes, sir.
Cool. Awesome. I think we're about to time out. This is a perfect place to stop. The power rule is by far the most annoying rule to prove, and it takes a while. But I hope you guys understand it. All we did is found patterns, and we used those patterns to kind of poke at the rule and make it come out of the closet. All right.
Yeah, I'm just writing it down real quick. The meeting's probably going to end.
Yeah, okay. So the meeting's going to end in just a second. You guys can come back in 10 minutes when the meeting ends, and we'll continue. This is a good stopping point.